All right. So let me start off. This is going to be a slightly complicated talk because we've been working on the code for a bit. And as we'll try and show you in a little bit, you'll see that the portions of the code that we've tried to integrate are something that a lot of other speakers have spoken about at NANOG earlier. And we'll try and show you how those pieces integrate. But one of the things that I wanted to start off with was the idea around test-driven both development as well as deployment, and sort of our own incursions into what we've been trying in this space. So to begin with, I'm Akshat Sharma. I'm a TME at Cisco, and we handle a lot of web service providers in general as our customers. And the reason I mentioned that is primarily because of the scale of the operations that we have to deal with when we talk to them for all of our equipment that we sell them. And the reason most of this tends to become important is because some people may assume that network deployment is pretty straightforward. When you start off, you really just have to purchase your devices, go ahead, have your truck rolls, get to your installation sites, and from there on, it's pretty much just automated NetOps, right? You've got a bunch of config management tools, possibly combining with your network devices if they're supported, and that should eventually lead to service activation. So that seems pretty straightforward. But you usually have a little bit of pre-staging that goes along with this. So let's just imagine that you would purchase your devices, but you would probably want a little bit of pre-staging before the truck roll eventually leads to service activation. So that's fine too. Probably another stage gets added. But then maybe we need a bit of monitoring and some hands on deck in case things go wrong. Some more truck rolls when devices fail, and a few more people who know what's going on the devices. So I think what we're really realizing is that network deployment is complex. To start off, we always think about some of the granular pieces of what's actually involved in network deployment. And what we really realize throughout the process is that validation and test cycles, both during the initial phase of the development of features from vendors, as well as the initial validation and test cycles that the customers go through before they deploy the devices, tends to become extremely critical. Now, this can, by the way, take a lot of time. In most of the cases, we found that this could take weeks, sometimes months, based on how the deployment architecture is constructed. Certain customers like to be able to have multiple teams validate different pieces of the architecture before the entire deployment goes out. So there is a considerable investment on testing hardware and on good testers and developers. And that's something that we've seen both at the vendor side before the software is constructed and thrown out into the wild. And also, of course, on the customer side, where you have to have a lot of people who know what's going on in terms of the capabilities on the devices, as well as all of the deployment characteristics that they want to encode within the test cycle. So having understood that, let's try and deconstruct network test and validation a little bit. What we've effectively understood is that validation cycle requirements really want a representative test environment to be available when the validation cycle happens. And representative test environments are hard to do, primarily because if you deal with physical infrastructure most of the time, especially during test cycles, you're really never going to mimic your actual physical network. You're pretty much going to have a subset of what's going to be deployed, and therefore your entire test and validation cycle is not really representative of all the cases that you would like to be able to cover in actual deployment. In addition to that, there are time and cost constraints that tend to creep up a lot of the time, which we often like to consider as a core part of the deployment process, because deployments are constrained by timelines in general. So when you consider the overall time constraints, the same sort of time and cost constraints get applied to the validation cycles as well, which is what really shrinks down the level of validation that you can have during the cycle. So the general requirement tends to be that you want to be able to reduce the months to potentially weeks. That is definitely an initial goal. In addition to that, you want to reduce the man-hour investment that you actually have when you go ahead with these validation cycles. But more so, the capex on the test hardware actually hits a lot of the customers a lot of times. When you start considering that you have to have validation cycles on actual physical hardware, you are either spending more to be able to get your labs up and running, which, by the way, are also not representative based on what I was saying earlier, because physical hardware in general not only reduces the multiplexing that you can have with the number of people trying to test at the same time, but also the representation that you can have of the actual physical topology. But what we really want to be able to achieve is extremely exhaustive automated tests that take into consideration both the constraints that I just mentioned. Have representative test environments, consider the constraints in terms of time and cost, but having done that, split up all of your test requirements into 3 primary categories. Right, so you've got topographies, as we'd call them, or essentially scenarios within the test cycle that are dependent on the topology that you're running. Combine that with a bunch of different actions which are pretty much independent of the topology itself and may be executed directly on a host basis, and those could involve functional or negative tests. And follow that up with validations at every stage so that you effectively are testing all of the possible actions on all of the possible topographies and then potentially cover what you need to do before deployment. So if we try and look at this entire spectrum of things that we need to do before testing, you realize that with physical hardware, with the time constraints, and with generally the level of test scripts that we tend to write, none of these tend to be possible before deployment. And we want to be able to address that, but do this in a slightly more tool-driven fashion. So let's consider the problems at hand. We've got vendor network protocol implementations that are notoriously difficult to test. The reason I say that, it's because of a lot of custom vendor-specific APIs that tend to come in across vendors. Now, this is not just a problem in deployment, it's a problem in validation. When you start constructing your test scripts, this is precisely why tools like Napalm, etc. exist, because of the multi-vendor differences. And the lack of models is a pretty big problem. When you consider the fact that every vendor has their own API, you also consider the fact that in order to cover all of the possibilities that a protocol can expose to you, you are pretty much going on your own knowledge of what the protocol can do before you write your tests and validations. Now, the model which could be, by the way, in any given form factor, right? It doesn't need to be Yang models. It could be a .proto file. It could be plain written down indicators of what the capabilities of the protocol API are. And in all of those cases, you realize that without a set model of what a protocol or an API can do, you're pretty much left to your own devices in terms of figuring out what your test cases will be. So potentially leveraging any sort of modeled representation of protocols to be able to construct your own test cycles is probably a good way to look at these requirements. In addition to that, non-overlapping tool coverage is probably one of the biggest problems, and I already mentioned Napalm a bit, but consider the fact that in order to cover all of the possibilities in terms of config and things that you can do on the devices, at this point, if you start comparing all of the tools, Ansible actually comes pretty close to multi-vendor support, simply because it has the modules for all of the vendors. However, it's the integration that you have to think about. Ansible still has modules for different vendors in different form factors, which means that you still need some level of abstraction to include Ansible within your test framework. You can't just start writing the same tests differently for each and every vendor. So the real problem is that you cannot really commit to one tool over the other. Usually you end up using a multitude of tools, or at least start splitting up your tests across the deployment topology so that you can test different vendors at different times, which again increases the time that it takes to actually test your requirements. So having considered all of these problems, let's just make a statement that if we have to construct a test framework that works, we need it to be modular. And when I say modular, it means that each of the pieces in terms of the way it talks to the devices, the way it represents the APIs, the tools that it internally uses, should be potentially swappable and replaceable at every stage so that it can pretty much pick up the tool necessary to talk to the different vendor as needed. So let's consider how we would potentially try to create an open source test framework. What we decided to do was take a look at a list of tools that are available and try and address the requirements at a higher level. We want our workflow and tool selection to never be sort of bound by architectures. Whenever and this is probably a bold statement to make, but the reason we don't want it to be bound by architectures is because if you go ahead and say that your certain set of tools are going to be used within your test framework, you automatically limit the capabilities that you have with respect to multi-vendor engagement. And we wanted to make sure that if the tools are replaceable and swappable at every layer of the test framework, then you should be capable of designing tests at a higher layer and allowing the lower layer to talk to the devices as needed. And we'll keep the stack modular and composable, which feeds into the initial point that I made. And we'll reuse existing industry tools. So let's not try to create a whole new tool from scratch. We'll try to go ahead and leverage the tools that are already available, fit them into a larger architecture, again within a tool framework that already exists. And then from there, we'll start building out the actual pieces of the test framework, which are test representations and models that will get us to a point where we can leverage the tools to test every piece of the protocol or the API. And finally, having done that, we'd like to be able to create a community to share test cases and extend libraries. This is notoriously hard to do. When you consider that test cases ought to be shared, you have to realize that test cases today are written in some form of code. Right? It could be in Python, it could be in C, Golang, doesn't matter. But if you've written your code in one way, somebody else that needs to potentially look at those test cases, extend them, or deploy them, would have to understand your code, the way you've written it, and try to then go through that entire process before they can add any sort of extensions. Now, that inherently makes the concept of test cases not really shareable. We wanted to create a higher abstraction for it, again using existing tools, so that we can represent the test cases in a way that you can share them as text files, post them on GitHub, allow people to reuse the test cases, and let the underneath layers sort of take care of how devices are spoken to. And of course, stand on the shoulder of giants. We've seen a lot of the stuff that the Open Daylight community, or now the FD.io community has been doing. And they've adopted most of the tools that we decided to adopt as well. I'd actually really implore a lot of you to go and check out their Git repositories, check out their integration tests in terms of how they write it. I believe the tool selection has been right. But of course, they are time-bound by their own requirements, so they may not be looking at creating a shareable test framework in general. However, it is representative of what you might want to do if you want to create a shareable test framework. So let's just keep these items in mind as we try to construct the different pieces going forward. So let's create one piece at a time. One of the things that a lot of testers in general spend a lot of time on is actually their setup of their topologies. And this is something that we've known for a long time, something we do not really address except for letting test teams handle it on their own. The fact is that the initial setup before a test runs and the potential cleanup that may be needed after every test runs is the pretty much the piece of the test cycle that takes the maximum amount of time because there are errors in there caused by the test framework itself. Nothing to do potentially with what you're testing, but with what you're actually testing with. And if we start considering, therefore, that in the end, your network is just a graph with a bunch of nodes, an undirected graph at that, then we'll try and represent this in pretty much a representation that most people are comfortable with, YAML or JSON. And we'll look at it as a pure graph that we'll try and assign attributes to going forward. Okay. So topologies. One of the first things we did was create a schema for how you would represent a topology. Now, this is nothing to do with orchestration tools or any given a validation mechanism in general. All we wanted to do was that if we go ahead and adopt a YAML representation or a JSON representation, you should have a schema that goes with it so that you can validate that somebody providing a topology to you fits a particular standard. This standard could be flexible, right? We're not going to claim that our standard is the way it should be. But if you're defining a schema, stick to it and allow people to contribute using that schema, the other topology files. So what we essentially do is construct a schema which represents all of the different fields that you can have when you represent nodes and edges in a graph. And in addition to that, we create the YAML file which then has to meet those requirements. And then finally, run tools like PyQualify, etc., to validate the topology against the schema. That's the first part. Now, this particular topology is representative of either physical or virtual hardware. It doesn't really matter. As long as you're able to represent it in the correct format with the characteristics of the node indicated there, then it should be validated as easily as any other. After that, we go on to the orchestrator piece. The orchestrator piece is actually critical. We spoke about the fact that most of our testing tends to happen on physical hardware because in the end, that's how vendors deliver a lot of their software because it's tied to the hardware that you're running on. Also, the fact of the matter is that you do want to be able to test your sort of platform independent features or protocols independently from the actual hardware, but you don't end up really doing that. Most of the time, we see people doing the actual platform testing and the platform independent testing pretty much on the same lab or the same topology environment. And that pretty much means that you're tied to that topology at any given piece of time. So trying to look at platform independent or protocol level testing as something that is completely independent of actual physical hardware allows you to then construct virtual form factors that you can run your tests against for your protocol independent stuff, and then combine that with parallel testing of platform dependent stuff, which would require actual hardware. So there is a lot of parallelization that can potentially happen once you start looking at what the capability is with virtual representations. Now, we've actually got a lot of virtual form factors available from all of the vendors. If you've taken a look at what's available now, protocol independent representation has become pretty good. And that is actually in line with some of the other tools available like NetSim, etc., which are more idealistic representations of what the protocols ought to be. But the individual vendor-driven virtual form factors are more representative of what the vendor is able to deliver for that protocol implementation. So having considered that, we construct the orchestrator in such a way that a validated YAML or JSON file through the PyQualify mechanism is able to feed into the orchestrator, which can then choose whether to launch a virtual lab or simply create connection objects for an existing physical lab as you may please. And as part of that, we also incorporate the verified topology piece. This is something that some of you might have actually heard yesterday as well, where we spoke about using packet injection as a technique to verify topologies. We wanted to move away from things like LLDP or any protocol implementation that a device may need to actually verify connectivity between devices. Thankfully, since most of the vendor devices are now Linux-based, we can pretty much use raw sockets to be able to inject packets and figure out if the packets are able to reach the other end to see if the topology connection actually is valid. So we incorporate that as part of the orchestrator cycle itself. And eventually, if the topology has been verified through YAML and JSON using a schema, has been launched or has just been connected to based on whether it's physical or virtual hardware, and it has been verified based on packet injection, then all of these techniques at this point allow you to make sure that your entire setup is up and running based on your requirements without dependency on any sort of vendor-driven protocol whatsoever. So at this particular stage, it should work identically for all vendors as long as they are Linux-based. And then, of course, comes the test framework. There are dozens of test frameworks that are available. And some of you would be aware of a lot of the behavior-driven test frameworks, especially things like Cucumber or Python Behave, etc. Or if you are more on the RSpec side, you would have similar examples there as well. You would effectively consider keyword-driven tests as another category, where I won't get into details of how each of these test frameworks work, but the indication is pretty clear that you've got test frameworks that follow different types of mechanisms based on what people are comfortable with. And these test frameworks have been developed in completely disjoint industries, right? So there are people on the server side, web developers, etc., that have developed their own test frameworks for what they feel is very representative of their requirements. And remember that we wanted our test cases to be inherently shareable. Writing a test cases in code makes that a problem. And therefore, we decided to make one bold assertion, which is test cases should not be written in code. If you're able to go ahead and separate out the requirements that a tester has before they write their test scripts versus what the actual library exposes to you, then you can start looking at test cases as pure text files or combinations that a tester can come up with on their own. So keyword-driven tests is what we decided to go with eventually. And for us, robot framework worked really well. Some of you might know the history of the robot framework. It came out through Google quite a while back. And it was constructed primarily to address a lot of web developer requirements. So one of the first libraries that came out for it was the Selenium library that folks used to be able to test their implementations of their websites, etc., and write robot framework tests for that. So having understood that, this is how we decided a test suite structure should therefore look. This, by the way, mirrors what I was mentioning earlier, which is you need to have topography scenarios, which are based on a given topology that you're running on. You have topology-independent actions, and then you have validations of the entire scenario. You may even have validations per topology-independent action as part of the system. Now, having understood this structure for a given test suite, what we really wanted to do was expose keywords for potentially all the actions that you can take, either on a topology-independent fashion or in a topology-dependent fashion through keywords. And keywords inherently allow you to subscribe to what the library is exposing to you. If you don't like it, go ahead and contribute to the library to extend its capability and introduce new keywords. That's fine. But as long as the library remains consistent for folks to use, the upper layer, which is described in the form of keywords, will be easily shareable and extendable. So these test cases are what we want to be able to eventually share with the community. And therefore, having understood how those test cases can then be represented in the form of keywords, we wanted to then leverage all of the model-driven representations of protocols that we have today, and I'll get into that in a bit, and construct the libraries required for the robot framework to expose these keywords externally. While underneath, we want to be, remember, modular. Right? So we don't want to go ahead and subscribe to one particular tool because that tool might not work with some of the vendors. So YDK-Py seems like a good choice because it goes ahead and builds on Yang models and gives you Python objects directly for all of the Yang models that are available, whether they're OpenConfig, vendor-driven, or IETF. But there are some vendors that don't support Yang models. So what do you do with that? So in that case, you have to consider other implementations, Napalm, lets you do a few things, not everything, but you can always keep extending its capabilities. And then, of course, Ansible, something I mentioned earlier. Ansible seems to have a pretty much a multi-vendor driven implementation today, and seems to be extending pretty fast. But having said that, none of these implementations need to be tied to the framework. So as long as you're able to represent what the actual actions and validations need to be at a higher level, you can then start constructing the lower pieces separately. So we haven't done this yet, but in the next generations of the code, we'll try and replace the lower half, which talks to the devices, in the form of a shim layer, so that different vendors can then contribute their own representations of those keywords. And therefore, if we bring it all together, we wanted to be able to divide the requirements into 3 pieces. So you've got testers that eventually will look at only the keywords that are exposed by framework libraries and allow you to be able to use the topography scenario sort of combination of test cases to make inherently shareable test cases in that format. And if they are shared in that format, subscribe to certain standard topologies and then potentially extensible to other topologies, then you get a way to be able to leverage community-driven created test cases at any given point. And the framework developers, which by the way is not that complicated because all of it is actually done in Python, these framework developers would like to be able to create the keywords for you by initiating the MD-test library construction within the robot framework. In addition to that, the orchestrator piece, which also could have its own ways of testing out your topology, verifying, etc., and should be extensible, will be part of the framework development process. And then you come to the actual device or system under test, which can be potentially any vendors once you're able to construct the library to a large extent. Right, so let's consider this. By the way, I'd like to be able to show you this entire demo, except there are certain parts of it that don't work yet. But I'll try and show you certain pieces of it that we can cover right away and try to showcase what's happening. Okay, we can switch. Okay. So having understood that, let me show you a couple of the pieces right away. So the first part that I spoke about earlier was essentially the topology verification that I'd like to be able to show first. Now within this system, what we've done is open sourced 3 different parts of the architecture. There is the orchestrator, the topology verifier that we mentioned, and the robot framework piece itself that currently integrates with Napalm, NetMiko, and parts of YDK. And we want to be able to extend that further. As part of the orchestrator system, we effectively have, sorry about that. So at this point, what I can do is initially go ahead and spin up the initial validated YAML file, which goes ahead and spins up Linux instances to showcase how the topology would work. Most of these Linux instances boot up pretty fast. So as they boot up, all of the representations of their connections, etc., will be automatically converted into Ansible host files. And we'll effectively leverage Ansible to be able to construct all of the steps required to launch your topology, to verify your topology, and then create connection objects for you at the end once the topology is verified. So I'm showing you each of the pieces separately at this point, primarily because we want to be able to integrate robot framework into our Ansible playbooks as well. And once that happens, the entire cycle becomes a single representation of what we're doing. Now, while this topology loads up, What I also have is an initial topology already running with a bunch of XR instances as examples, primarily because of their Yang-based support. And give me a second. Good. All right. So much of this implementation has already been open source, and what I'll show you while that goes on is the GitHub repository or the organization that you'd like to be able to visit. The project is currently called RoboYDK. We're thinking of other names, but primarily because the model representations of the APIs are YDK based, we've decided to go with that name for now, but we'll probably try to update that later on. The three pieces that you're probably interested in are the RoboYDK, Orchestrator, and Topo Verify. And each of these pieces work together and are run within an Ansible playbook. Now, as part of RoboYDK, what we've done is gone ahead and open sourced some of the libraries that we deal with on a day-to-day basis. And these include things like Napalm, NetMiko, and the support for YDK, which is in a separate folder here. And the way we work with this is that once the topology is up and running, we use NetMiko and Napalm to be able to push the initial bootstrap config on all of the nodes, and then finally utilize YDK to be able to construct our model-driven test cases on top of that. So our protocols would be tested based on model-driven APIs, whereas the initial bring-up and the connections to the devices would be done using multi-vendor-driven tools like Napalm and NetMiko. So all of these tools have effectively been represented further up as keywords, which would be available within the robot directory. So as an example, for the Napalm library, all of the normal function calls that Napalm exposes are exposed further up as keywords that become available to direct testers. And this is pretty much where the keywords start becoming useful. Once you have these keywords available, you want to be able to construct your test cases purely in the format that the robot framework exposes. And these test cases are pretty much able to cover anything that you would normally do with a Python script, but never actually having to write the code for it. As a quick example of what's happening in the background, okay, I'll quickly wrap this up. So this, as an example, is a very basic keyword that we expose upstream. What it does is it utilizes NetMiko and Napalm keywords internally to be able to set up all of your devices under test in one go. In addition to that, once we go further upstream, within the topo dependent set, we're able to actually utilize things like the setup DUT that I showed you earlier within the system to be able to create a test setup, which I had just commented a little while back. But it allows you to set up all your DUTs before the test starts, and then represent each of the test cases, like configuring IP for BGP, etc., using the Yang models underneath within the test cases. I know I'm not able to, purely because of time, I'm not able to go through all of the pieces at this point, but I would definitely encourage you to actually try out some of the pieces that we have on GitHub already. There are Vagrant files that we've published, and you should be able to bring them up and see how all of it works. But of course, if you have any questions, please go ahead and come by, and we'll be happy to answer that.